First section, section 2.1. So our first unit, there are 5 sections in chapter 2 that we're going to do in the next couple weeks. They all kind of deal with this same topic. This is my favorite unit of the class, just because when I was in college, when I was doing what I did, I majored in set theory, which who knew there was such a thing as that. So what we're going to talk about in chapter 2 is we're going to talk about sets. And particularly in this first section, we're going to deal with just some set concepts. We're going to get familiar with the terminology, some basics, the behavior of sets and how they work, so that when we come back next week and we talk about how sets interact with each other and the operations and then some applications of what we can do with them, we'll be totally familiar with those things. So the first thing I got to tell you is what a set is, because I'm not expecting that you have any knowledge prior to what we're talking about today. So what a set is simply a collection of objects. Doesn't matter what the objects are, you're just grouping them together. And normally when you write down a set, you use braces. So these squigglies right here, not parentheses, not brackets, you use braces to indicate a set, okay, almost all the time. If I start going too fast, because I do get excited, I enjoy what I do, let me know, I'll slow down, okay? So trying to make it so that this is a good experience. So these objects that are in the set, they have names. I will either refer to the objects in a set as a member of the set or an element of the set. Those two terms are interchangeable. One is neither better than the other. So on your page, I have written down 4 examples of sets. I'm going to write them on the board just because we're going to do some things with them. So I'm not writing these things down to bore you. I just need to have them so that we can deal with them. So notice in each set gets a name. This first set I've cleverly named set A, okay, because I'm real creative, and it's just the numbers 1, 2, 3, 4, and 5. Set B, just to show you that it doesn't always have to be numbers in your set. I've got a collection of shapes. So I've got a triangle, a circle, and a square. It took me a long time to find those in Word. Set C is the set of days of the week. And then set D is the set of best ice cream flavors. Again, I know you're reading those. You don't have to write those down, but I just want them on the board so that we can refer to them. Okay, so the first thing I'm going to tell you about a set then, the first attribute of it is we can have what's called a well-defined set. Okay, so a set is well-defined. That's the next blank on the sheet. Okay, a set is well-defined if its elements are not subject to opinion. So the importance of that is a well-defined set means that it's going to be the same set whether I'm looking at it or whether you're looking at it. Okay, so it's going to be something that's clear. It's not going to be something that changes. Okay, so for the 4 sets that we have over there, set A, B, C, and D, 3 of them are well-defined and 1 of them is not well-defined. Which one would you hypothesize is the not well-defined set? Which one? Why? Perfect. D, because it's not specific. It's subject to opinion. What does best mean? Well, best means that all of us are going to have a different set here. I mean, I'm a vanilla guy. I find that fascinating, but you might not be. You might have to have some other things in your ice cream. Okay, so all of our sets here, if I asked everybody to list down their favorite ice cream flavors, we're probably going to have 15 different sets of ice cream. So on our sets, this one is well-defined. This one's well-defined. So is C. And then lastly, D. D is subject to opinion, so it is not well-defined. We good so far? Does everyone see the difference between a set being well-defined and not well-defined? Remember, the second you have a question, please ask it, because the question you have, somebody else probably has, and want to make sure that we're getting all these things cleared up. So I've got a quick exercise for you right below. I've given you 2 more sets, so I'm just going to give you 20 seconds. Write down next to each of them, is it well-defined or is it not well-defined? Okay, so the first one, if this is your thing, Academy Award winners in 2018, is that a well-defined set or a not well-defined set? Well-defined. We can do a Google search and we're all going to come up with the same winners. Okay, so this one here, this is well-defined. How about the most interesting professors at Polk State? Not well, even though the Perkster would be in everyone's set, I totally understand and appreciate that. This is not well-defined. Some of you might just be an empty set, okay, because there's no interesting professors, and that's fine too. I noticed I skipped a couple blanks because I got excited there, so just got to go back up. I need to tell you another attribute of these sets. Okay, set A and set B. Set A and set B are written in what's called roster form. What roster form means is you list out all the elements of the set. So A and B are lists. C and D, these are kind of the lazy mathematician's way to write down sets. It's not used abundantly, but it does give us the way to write down sets quickly. These are just in descriptive form. Not very mathematical, but useful to help us as we're learning about our sets. So both of these 2 examples here that we just went through, they're also just in a descriptive form. Are we good here? Can I erase this? Everybody, any questions? Again, well-defined, not well-defined. Do you see the difference between roster form and descriptive form? Are we doing okay? Don't want to leave anybody behind on day 1. Okay. Well, then the next thing, the next attribute, so we've seen what makes a set well-defined and not. We've looked at a couple different ways to write a set. There's going to be one more way to do that we'll talk about when we flip the page. But the next thing is the idea of what makes a set, the size of a set. And so a set is finite. A set is finite under 2 conditions. It's finite if it has no elements, so if it's empty, or a natural number of elements. Now, you might not know what the natural numbers are. That's okay. Again, I'm not assuming anything. I just didn't have a good order to introduce the idea of the concepts of finite or natural number. If I did finite first, then you don't know what natural numbers are. If I did natural numbers first, then there was another thing. So I'm just doing the best that I can here. So a set is finite if it has no elements, or if basically if you start counting the elements, you're going to stop counting. So all of the sets that we have so far are finite. Set A, 1, 2, 3, 4, 5, it has 5 elements. That is a finite set. This has 3 elements, finite set. Days of the week, 7 elements, finite set. However many ice cream flavors you can think of, it's going to be finite. So whatever your set D would be, it's going to be a finite set. So one more thing, and then we'll do a couple little problems. So that natural number that we count to, that is called the cardinality of a set. The cardinality is the number of elements in the set. Probably the hardest thing about the cardinality to remember is the notation. When you take the test in a couple weeks, whatever day that is on, there's going to be at least 2 problems about the cardinality. And basically, you just got to remember this notation. The way you ask for, or the way you denote the cardinality of a set is like this. So if I'm interested in what the size of this set is, meaning what's its cardinality, I will ask it like this. I will say, okay, lowercase n for number. And then in parentheses, I will put what's the set we're talking about. So this says the number of elements, the cardinality in set A. And what are we going to write down? What's the number of elements in set A? Yeah, I just told you that. So there we go, 5. So real quick, I'm going to give you 15 seconds. Answer that same thing for set B and set C. I've got right there below in that exercise, right below the blank for cardinality. What's the number of elements in B and what's the number of elements in C? Just to get used to writing these things down. All right, what did you write down for the number of elements in B? Perfect, great. You can do this, then you've already got 2 problems right on the test when it comes up. How about for the next one? What's the number of elements in C? 7. I had a question in yesterday's class, because I do this same class on Monday and Wednesday, and somebody said, can't we answer that for D? And the answer is we can, but we would have to define what D is. And as I said earlier, set D is going to be different for everybody because it's not well defined. Okay, so if you were interested, then you would write down, okay, what are my best ice cream flavors? You list it out, then you could define the cardinality. So that's why I didn't ask about that one. All right, so there's another exercise right below that. I've defined a set D. So I would like you please to write down, I'm going to give you 15 seconds. What is the answer to this right here? What are you going to write down for in parentheses D? And what is the answer to this? What's the cardinality of set D? 10. Perfect. We doing okay? Okay, good. I want to make sure that is going to stay true. So I told you earlier that if a set is finite, that it can be associated with a natural number. And I then said, okay, I will tell you what the natural numbers are. So now is that time. The natural numbers are these numbers right here. They are denoted usually with a capital N. Usually it's bolded, but I don't really have the ability to bold here. So we'll just use a capital N. N for natural numbers. And the natural numbers are this set right here. They're called the natural numbers because they're probably the first numbers people used thousands of years ago when you count your fingers. Okay, so we've got 1, and then 2, and then 3, and then 4, and then 5. And the natural numbers are the first infinite set that we have. Okay, so if something's not finite, it's infinite, meaning it never stops. And so I don't have enough time to keep writing down an infinite set of numbers. So what I'm going to do is I'm going to write 3 dots right here. Does anyone know what those 3 dots are telling me? Continue. Yes, keep following that same pattern. And what these math people name everything. Sorry about that. These are called an ellipsis, in case you're concerned about the trivia. And what they tell you is just to keep following that pattern. And the pattern is you just keep adding 1. You can do that forever. So the number 35 is a natural number. The number 1,402 is a natural number. Notice we don't have any decimals, no fractions, no square roots, nothing. The natural numbers just count by 1s. So when we say that something is associated with a natural number, that's what we mean. So here's what I would like you to do. There's another exercise right below that. I've given you the description of a set once again, and I would like you to write that set in roster form. And it is, write the set of natural numbers less than 10 in roster form. These next couple of problems, we're going to look at our reading comprehension. Just make sure we are reading what's there and not what we assume. That's a great question. Will 0 count? Well, I asked for natural numbers. Where do the natural numbers start? 1. Excellent. If we added 0 into that, that would be called the whole numbers. And we're just going to, I don't want to get too complicated. We're just going to limit ourselves to the natural numbers. Then after that, if you make them negative, you got integers. Then we got decimals, you got rational numbers. So the exercise is to write this set of natural numbers that are less than 10. So because they're natural numbers, where's this set going to start? Okay, 1. And then since it's less than 10, where is it going to stop? Perfect. Love it. Great job. It's going to stop at 9. Less than means we're not including the end. If I did want to include the end, if I wanted the 10 to be there, what words would I add in? It would be less than or equal to. Yes. Okay. So don't assume. Okay. Make sure you're reading and responding to what is written. I'm turning to page 2. I would like you to do the next exercise. Same sort of thing. You're going to write the natural numbers between 3 and 12 in roster form. All right, so I'm just trying to give you a look of the different things that you're going to see. What does the word between mean? What's the significance of that? Doesn't include them. So if I ask you for the set of natural numbers between 3 and 12, that means we're going to start where? 4, and we're going to go all the way up to? Excellent. You're doing a great job. I really appreciate that. By the way, if you do miss one of these problems, don't beat yourself up. We're here to learn, so mistakes are chances to learn. If you already knew all this, then there'd be no reason for us to get together, okay? So don't get down on yourself. I did give you the alternative. If I did want to include those endpoints, the 3 and the 12, the next exercise is write the set of natural numbers between 3 and 12 and circle the word inclusive. That word means now you're going to include the endpoints. So just go ahead and take a moment, do the tactile bit and write that down, and then we will continue. So we're writing down the set of natural numbers between 3 and 12, and then the word inclusive is there, so that changes it. So I'm now going to include the endpoints. And there it is. We're still doing okay. Anybody got any questions for me? Anything I need to clear up for you? All right. Well, probably what we're going to spend the bulk of the rest of our time on is the other way to write sets and a couple other relationships. So we talked about roster form, which is just listing things out, and that's what we were doing. Then we talked about descriptive form, which is kind of the not mathy way to write sets. The other way to write sets, and we're not going to use it too much. We could use it a lot in this class, and I'll show you a couple different places as we go through this chapter where we could define things using this. It's called set builder notation, and I've given you kind of a very generic example of it. I've written down this. So here's how set builder notation works. If you're reading it, because I know math people love symbols and it's just a whole weird language. So when you see the brace, you say, okay, this is the set. Okay, so when I'm saying this, I say this is the set. I've got an X here. Now here's the thing. This is where we're going to limit ourselves. We're going to, in this class, we're only going to ever have an X here. If you went further and did some stuff with sets or different parts of math, you can change this up and kind of have you can have a different arrangement or a different relationship between variables here. But so this is just going to be the set of values. So what we've got is the set of values. This wall right here is pronounced such that. So we've got the set of values such that, and then the key thing, and this is the part where we're going to focus our attention on set builder notation, is the conditions. So over here, you're going to tell everybody what are the conditions or what are the attributes of these values that we're talking about in this set. And the value in set builder notation is it allows us to write very large sets in a little bit of space. So for example, I have an example right below. What we're going to do in just a minute after I tell you one other thing is we are going to write the set of natural numbers that are less than 100 in set builder notation. And now I'm not here to torture you, so we could write that out in roster form, right? And start at 1 and 2 and 3, and go all the way to 99, but that's no fun. It's not fun for me. It's not fun for you. Okay, so we're going to use set builder notation to do that pretty quickly. Before we do that, I have to tell you one more thing. There is a symbol that allows me to tell you, and you can tell me, if something is in a set. So for instance, if I want to tell my friends that the number 2 is in that set, then here's what we would use. We would use this symbol right here. It looks like an E with no corners. And this symbol right here means is an element of. Yeah, around E. Perfect. Good description. So if I wanted to tell somebody that 2 is an element of set A, then here's what I would write. I would write 2, and then the round E, and then the letter A. So this symbolically says 2 is an element of, or a member of, set A. So just to practice, okay, I'm hoping this is fairly clear, but I just want to make sure that we're feeling good about it. I want you to write down what you would say to tell somebody that a triangle is the element of set B. Okay, a triangle is an element of set B. Hopefully what you wrote down is something like this. You wrote down a triangle and an element of, so the rounded E, and then set B. So I don't have to write the whole set out. We know what set B is. It's been defined over there, so I can now do things symbolically. One more, just for kicks. Write down Monday is an element of set C. So I'm going to write down Monday is an element of, so the rounded E, and then set C. One more thing I'm going to tell you, just as we're learning to work with this. For set A, is the number 9 in set A? No, it's not. So we can tell people that too, that relationship holds. So it's just kind of like an equal sign. If you're familiar with your arithmetic, we can say the number 9. And then instead of saying it is an element, we can write the rounded E with a line through it. 9 is not in A. Just in case you see those things, which you probably will in the home. My goal is I want to leave you with all the tools that when you go through the homework, you know, oh, we saw this in class, everything's good. Okay, so that's my hope. All right, so I'm going to leave this here. Let's erase over here. My example, we are going to write down, we're going to do this one together, the set of natural numbers less than 100. And we're going to use set builder notation again. I already mentioned, don't want to write that down by hand. So it's the set of values X. Again, you're never going to have to think about that in this class. Okay, we're leaving that part. That part's going to not change. So it's the set of values X such that it adheres to these conditions. Well, there's 2 conditions up there. What's one of them? Okay, it's less than 100. That's one of the conditions. And what's the other condition on any element of this set? It's a natural number. We don't have any decimals, no fractions, no negatives, nothing like that. So those are the 2 conditions. So I'm going to address each of them first. To let everybody know that it's a natural number, here's what you're going to do. You're going to say, okay, this is the set of values X such that, well, each of the values is an element of the natural numbers that we just defined earlier. Okay, so you're just learning how to write symbolically something that we just said in words. Okay, so you're becoming more of a mathematician. Congratulations. I'm going to put a comma. And then this second part, you probably remember from arithmetic class. How do I write that something's less than 100? What's the symbol for that? Yes, we drew it. The gator, yes. Go Gators. So x is less than 100. There we go. So you've demonstrated the two conditions. So all of the numbers in this set are natural numbers. They're less than 100. That's the 1 through 99. And now I don't have to write all those values out. I've described them. You're going to do the same thing. It's almost identical. Okay, just one minor little change just to keep it spicy. So do the next exercise. The set of natural numbers less than or equal to 35. So this is going to be the set of values, x, such that, give me one of the conditions. I'm sorry, I didn't hear what you said. Perfect, thank you very much. X is a natural number, and then it's less than or equal to 35, so the symbol is x is less than or equal to 35. You might have the question, hey, Perkster, could I have just said, instead of saying less than or equal to 35, could I have said just x is less than 36? Since we're dealing with natural numbers and there's no decimals, there's no numbers between 35 and 36, yes, you could have done that because we're dealing with natural numbers. Okay, so either one of those answers, if it didn't even occur to you, then don't worry about it. But if you had written this down in my class yesterday, I had a couple people that wrote that down, so I just want to make sure that I address that. The next one you can probably do on your own, but I'm just going to make sure that we understand how to write these things. So the set of natural numbers between 5 and 50. This is the next problem. Beginning of this, no different, set of values x, such that, and then in fact, since it's a natural number, x is an n. But the second part, the between, I just want to make sure, I don't want to assume too many things about your prior math history. Okay, so when we want to write that a number is between two values, here's what we're going to do. I'm going to leave a little space here. I'm going to write my x. So between 5 and 50 means my values are both at the same time, they're bigger than 5 and they're less than 50. So reading from the perspective of the x, if I go this way, my x's are bigger than 5. And then again, reading from the perspective of the x, as I go this way, the x's are less than 50. So this is my betweenness inequality. Okay, the x is in the middle, and when I read it from that perspective, the x's are bigger than 5, and at the same time, the x's are less than 50. And that's how we can write that all as one statement. Just so you can practice, the next example is very, very similar. So write down in set builder notation the set of natural numbers between 2 and 25. Yep, when you see that symbol, as you do it more, your mind will just say, okay, x is an element of, or x is a member of the natural numbers. Yep. All right, so this one, set of values x, such that x is a natural number, as we've done every time. And then since it's between 2 and 25, the x's have to be bigger than 2. And then at the same time, they're less than 25. And there we go. There's my betweenness. One more of these, just to make sure that we remember what this word is from earlier in the class. The next exercise says the set of natural numbers between 10 and 99 inclusive. Only difference on this problem versus the previous ones is because of the word inclusive, I now put these equal signs here because I am now including those endpoints. So not only is the x value bigger than 10, the x value can be equal to 10 now. So I use that symbol. Same thing for the 99. Not only is the x less than 99, it can be equal to 99. So there's our conditions. The next exercise, we're just going to now practice reading the roster form. Reading the set builder form. So if you would, in the next exercise, write down what that set builder is in a roster form. This set says just what the other ones have said. X is a natural number, which is good because I don't want to write down a bunch of decimals or anything. And then the x's are less than 9. So that means they're going to start where? 1 and then go up to, perfect. Great job. You're doing fantastic. You're almost to the finish line. You're going to survive day 1, only 31 more days together after this. Do the next one, please. Same thing. You're taking that set builder form and writing it in roster form. So once again, I've got my natural numbers. They are bigger than 8. At the same time, they're less than 16. So those are the numbers that start at 9, 10, 11, and then go up to 15. And there we go. There's our answer. This next problem is just a challenge problem. Just again, I want to make sure that I give you a taste of everything you're going to see in the homework when we go through these in class together. So I've given you the set 5, 10, 15, 20, 25 up, and you see the ellipsis, so the pattern keeps continuing. I want you to write that in set builder notation. You're not going to be able to be quite as mathematical as this, so you can be a little more descriptive with the other characteristic. Give it your best shot. Okay, if you don't quite get it, remember, that's okay. We're here to learn, and I just want to give you an example of this. So I'm going to give you 30 seconds to chew on that and see what you can make of it. Okay, so the set starts at 5, it's got an ellipsis. So there's 2 characteristics of these numbers. What's the first characteristic? It's the same one we've been doing a lot of. They're all natural numbers, right? So the x's are natural numbers. Now this is the part I'm guessing you know what the second characteristic is, and you just might not have known how to write it down. Okay, so what else do all of these numbers have in common? They're all multiples of 5. Yes, so we're going to write that nice and simply, just as a little bit of description. X is a natural number, and x is a multiple of 5. Now, somebody in my class yesterday said, hey, Perkster, is there a mathematical way to write this? And there is. You in no way need to remember this. This is not part of the knowledge of the course, but in case you're curious, because somebody was curious yesterday, if you want to write that, that x is a multiple of 5, this is the mathematical way you would write this. You would write that 5, and this symbol means divides into x. So 5 divides into x. That would be how you'd write that in case that was too many words for you. You do not need to know that. That will not occur in my math lab. That is just extra bonus information to reward you for being here today because math is amazing. All right, we're almost done. You're doing great. Just a couple more things. If two sets have the same members, they are equal. The symbol for equal in sets is the same as the symbol for equal in arithmetic, just an equal bar. No different. That's a really great question. I'm going to answer that in just a minute. Okay, so I love that you're thinking ahead and processing this. That makes me super happy. I'm going to write down the 4 examples I have. And then if I don't answer any of those curiosity questions, please let me know. Okay, so these are the 4 examples that occur immediately following that definition. And so the definition of equal is if two sets have the same exact elements, okay, they are equal. So these first two, A, B, C, B, C, A, different order, answering your question here in just a minute. Would you say these are equal or not equal? They have the same elements, right? The definition of equal doesn't say anything about order, doesn't say anything about how many, it just says they have the same elements. How about the next one? We got A, B, C, we've got 1, 2, 3. Are those two equal or not equal? Not the same elements. The next one, I've got 1, 2, 3, and then I've got 1, 1, 2, 3, 3, 3. Would you say those are equal or not equal? This one's probably the one that'll surprise you a little bit. Do they have the same elements? Equal. And then the last one, A, B, C, D, and A, B, C. Are those equal or not equal? Not equal. Why? The D. Yeah, exactly. So don't overcomplicate these things and read into it. You're doing great. Love it. All right, one more definition and then just a couple more problems. And then you're going to be free of me for the day. And if you have any questions at all that you need to talk about, please bring them up. Don't leave here unsettled in any way. So the last thing about sets is if two sets have the same cardinality, then they are what's called equivalent. The symbol for equivalent looks like an equal, except there's 3 bars, so 1, 2, 3. So notice equal says they have the same elements. Equivalent says I don't care what the elements are, I just care how many of them there are. So just real quick, I'll follow up in just a minute. I'm going to give you 15 seconds. Equivalent or not equivalent for each of those. There's 4 different answers. It's the same pairs of sets as we did with equal. Each of these, are they equivalent or not equivalent? Equivalent sets have the same cardinality. Remember, cardinality means how many elements are there. So A, B, C, B, C, A, equivalent or not equivalent? Equivalent, same number, 3 elements in each, equivalent. A, B, C, and 1, 2, 3, equivalent or not equivalent? Again, equivalent, they both have 3. The next one, 1, 2, 3, and then 1, 1, 2, 3, 3, 3, equivalent or not equivalent? Yeah, this one has 3, this one has 6. The cardinalities are different, so not equivalent. And then last but not least, A, B, C, D, and A, B, C, equivalent or not equivalent? Not. Again, one has 4 elements, one has 3. Cardinal equivalence is all about how many elements are there? Do they have the same number? Last but not least, I've got one final exercise. I've given you a set E. It's the letters A through H. And then I just asked you 5 quick questions just to review the concepts that we've talked about to make sure that they are set in stone in your brain. One of those is going to be surprising, maybe, and the last one I've asked it to prepare us for what we're going to talk about next week. So give your best shot at each of those, and we'll talk about them before we pack up. First question. Set E. Is set E finite or is it infinite? It's finite. In fact, it's finite, so I can find the cardinality. What is the cardinality of set E? 8. Everybody tracking with me? Just going back through things we've talked about previously in the class. This is a little review and wrap up. This symbol means what? Element. Is C an element of E? Is Z an element of E? No. Okay. Then I wanted to leave you with this. The element of symbol means whatever you see here on the left, you can see within those braces up there. So this right here, squigglies with C in it, is this thing here, is that an element of E? Okay, that's what I was expecting. Okay. If I erase the squigglies, you are correct. There is a C over here. It is right there. But there is no object that looks like that exactly within the squigglies. There's a different relationship here. If I rewrote this set, let me rewrite it with the red ink right here. If I rewrite this set like this, A, B, C, now the answer would be yes, because I've got the C with the squigglies around it right there. So now it is an object inside of the set. Okay. So it seems like a little bit of a crazy detail, and I understand that. When we come back next time, the first thing we're going to talk about is what is the relationship between this and E, because there is one, and it's not element of, there's going to be a new relationship. Okay, so keeping that in mind. Other than that, we are done.